Well, we'll get started now. I think as many people are going to make it as can. I'd like to welcome you to the StatEase June 2014 webinar on I would really rather not randomize my experiment. And it's fine, you don't have to randomize things, provided you then realize that there's a special way to do the analysis. Two rules. Number one, if you want to understand the effect of a factor on a response, the factor must change during the experiment. And often it's not only most convenient, but also most effective to run industrial experiments without randomizing all the factors. Now, I would still rather you randomize some of the factors. In fact, it's more or less required. There are ways around it, but it involves lots of replication. Now, an example of one of those factors that's difficult to change is something like the temperature in an industrial-sized furnace. That's a common one. It's hard to change because it takes substantial time to heat and or cool the furnace for the next temperature treatment. So if you were potentially changing and or resetting the temperature every run, that would just make the time to run the experiment unsuitable to doing an experiment in the first place. So with a furnace, you're better off baking a batch of things in that furnace rather than just one thing every run. Make sense? That's what we're doing. So the design setup is you take the hard-to-change factor treatment combinations and you collect them into a group, and they stay fixed for a group of runs. However, if you can, take those groups and randomize them. And then the easy-to-change factors will be randomized in runs inside each of those groups. And it's the understanding of your grouping structure that is the key to doing the proper analysis. Without that well-understood grouping structure, you won't know the right way to do your testing. Get your p-values on the ANOVA, for instance. So for this example, we have an oven, and we're going to be using three temperature settings, 360, 370, and 380. And those is Celsius, of course. And we're going to be coating steel bars with a corrosion inhibitor. Sorry about that technical difficulty this morning. There we go. So the way this design gets structured is we have a group of 360s, a group of 370s, a group of 380s, and then back down the temperature gradient with randomized coatings. Basically, it's the order that they're put on the tray that gets shoved into the oven that are applied to essentially identical steel bars. The noise can come from different coating techniques being applied, differences in the steel bars themselves, and in the temperatures. It's very hard to get the same temperature profile even if I don't change the temperature. When you open the door, take out the old tray, put in the new tray, close the door, it's very hard to get it back to the exact same temperature profile even if you don't reset anything. Like I said, random order of placement into the oven, and then you set the temperature to your desired first run. And of course, don't forget to close the door. That will ruin your entire experiment. In this case, though, with your furnace temperature, it's not cost effective to randomize the groups. A pattern of, as you saw, 360, 370, 380, and then back down is adopted to reduce the costs. This can cause problems. The big one is when you don't really randomize and you have this pattern, it can also match it's more likely that it can match a lurking variable going on in your system. For instance, morning, afternoon, evening corresponds to the 360, 370, 380. What can change morning, afternoon to evening that might affect how well the coding adheres? There's a lot of things that aren't directly accounted for in the experiment. However, if you can do a good reset between each group, then you're going to be taking care of as much of that lurking variable problem as possible. That reset, opening the door, closing the door, setting the temperature dial back to some preset reset. All of those things will help you overcome this lurking variable bias. So, as I said, not randomizing the groups increases the risk of confounding the groups with a lurking variable, something that varies over time right with your factor changes. When a new group starts, even the factors that are not changing should be reset. So between those 380 temperatures, the door needs to open, the dial needs to be turned to the reset, the new tray loaded, turn the dial, close the door, turn it back to 380. If you choose to not reset the factors, then you've got another restriction on the randomization. It can make the analysis even more complex. You have to think about it. Make that determination. Is not resetting really representative of what happens in the truth? My rule is if you have to open a door, there's a natural reset in the process. But try to reset as much as you can. However, noise is caused by the resetting. Remember that first rule, you have to change things? Change that word to reset things, and then you'll be much better off. Easy to change treatments, reset every run. Hard to change resets, only reset at the end of their group. So you get one source of noise from the easy to change reset and a second from the hard to change reset. To account for those differences in the errors, there's separate half-normal plots. We're working with two-level factorials, and separate ANOVAs when we do the analysis that are created to handle the dual error of these designs. Your hard-to-change factor temperature, in this case, creates most of the noise in the process. It's very difficult to get the exact same temperature profile. In fact, it's probably impossible. Can't quite get the same profile is noise. If you don't account for this noise by using the correct analysis, it can conceal the coding effect. So I'll show you some of the analysis purposes right here. So a standard design is set up with this extra grouping structure added to it in our Design Expert software. And you can see that these groups are clearly delineated by these lines to separate the groups visually. Basically, anytime you see a line indicates you need to do some sort of a reset. The analysis, in this case, uses the standard old half-normal plot. Now, due to the nature of the way that the errors are calculated and created, it jumps around a little more than your standard half-normal plot. But basically what we get is, out of the easy-to-change factors, the coding makes a difference. It's not part of this error distribution. And the interaction between temperature and coding, which is an interaction between the hard-to-change temperature and the easy-to-change coding, indicates that the coding process depends upon the temperature where it's processed. Maintaining hierarchy, this A temperature gets selected to support the hierarchy of this AB. Now, is it significant on its own? Kind of a judgment call at this problem at this point. But we can take the information from the fitted model based on the half-normal plots and look at the statistical tests on the ANOVA. Thing to note is you get a different degrees of freedom, except in strangely organized circumstances, for testing the effects. It's only really a 6-run design, if you think of it that way, for the temperature. And a 24-run design for the coding. That's why the degrees of freedom change so much. Now, as I said earlier, if you choose to not take into account this restriction on the randomization, or if you really did randomize this experiment and included all of this hard-to-reset information in every run, then what would happen is you would essentially be ignoring the grouping structure. And when you do this analysis, it goes back to a regular old 24-run design for this system. And the coding and coding by temperature interaction falls into the noise. You literally are concealing the effect by not properly accounting for this hard-to-reset nature of the temperature effect. If you test it without taking into account that randomization, the temperature effects are tested with too many degrees of freedom. You really remember, it was only really changed 5 times, 6 runs. But if you try to test it against 24 runs of change, garbage in, garbage out. So, if the experiment requires restricting the randomization, take the time to set it up and analyze it with the best tool. Use those split plot designs. So what is a split plot? The word split plot design originated in the field of agriculture. Experimenters applied different treatments from factors such as the fertilizer, the irrigation, etc., to a plot of land. The same group of treatments is applied to the whole plot. The whole plots are then split, hence the name split plot, into subplots. And then within the subplots, things such as the seed cultivar used, the planting depth, are changed and tested between the subplots within a whole plot. If you want to work on the new treatment settings for the fertilizer and irrigation, then you need another field or another plot. The way this translates into modern usage is hard-to-change factors form the plots. Some factors are more difficult or expensive to reset, and these can cases, you conduct the experiment where the factors aren't really reset every run. Not all of them anyway. That restricting the randomization makes it more practical to run the experiment, but it creates a need for split plot design and analysis. There are some split plot designs that you can analyze by hand. It's expected mean squares, and you have to figure out the sources of variation and where they belong. When you get into less orthogonal designs, then you have to start using some fairly difficult to do techniques. At least they're difficult to do by hand. With modern computers, it makes a lot of the analysis problems go away. Now here's a thought provoker. Hard to change factors can be randomized. It just makes the experiment too expensive to run. When you're working with standard analysis, the assumption is the factor treatment combinations are randomly assigned to the run order and essentially reset every run. When you restrict the randomization, it allows the experiment to be conducted, but as I said, it creates a little more difficult analysis problem. The split plot design includes with it the proper statistical test shown on the ANOVA. The main differences between a split plot and a randomized analysis are the hard-to-change factor effects are detected with much less power. It's only a 6-run design instead of a 24-run design. And it's tested against the total, and the hard-to-change factors are tested against total error rather than the easy-to-change factors, which get all 24 runs of information and have their own smaller partition of the total noise. The proportion of the total noise that comes from resetting the hard-to-change factors drives how much the power differs from a randomized design. However, we really should look at this and approach, do I need a split plot design in terms of how much it costs to run the whole design versus the power of detecting effects. So with paper helicopters, it's one of our favorites around here, has lots of factors that can be changed. There's interactions between the factors that are fun to explore. But these paper helicopters essentially are cutting and folding a piece of paper and attaching a paper clip, climbing up a ladder, holding on, and then dropping the helicopter to see if you can hit a target. What gets measured is time to fall, which we want to try and maximize typically. That's the most fun thing. And then accuracy. How close to a given target on the ground can you hit? And it's a function of how the helicopter is constructed and how you drop it. So recently, some SATI's employees, Brooks among them, collaborated on a project and gathered some data via a split plot design. So what's hard to change about a helicopter? Well, honestly, all that folding makes my fingers hurt. And it's a fairly time-consuming and precise process. Cutting the tail, body, and folding the wings is time-consuming. And you have to be precise about it, otherwise you're imposing extra error in your system, and we all know that's bad, correct? So rather than making a new helicopter for every run, why not just reuse a helicopter for a number of runs? The construction factors are the hard-to-change set of factors. And by using a split plot design, we can do just exactly that. Use the helicopter multiple times. Maybe you should call it a split prop design. Setting up these designs is not really that difficult. We have a new interface for dealing with the hard-to-change factors when you build a split plot design. You choose your total number of factors, choose the hard-to-change factors, and set the number of runs that you can afford to do. And we will check power as we build the design to make sure we've got enough information. So for this design, 6 factors are being chosen. There's the 4 construction factors that are the hard to change, and then the 2 dropping techniques. A half fraction, 2 to the 6 minus 1 is the size of the design. However, we're going to be keeping the hard to change factors as a full factorial design. It's really 4 factors done in 16 runs, and then we fraction the easy to change. The 4 hard to change factors are set up in a structure that's identical to a regular 2-level factorial design. So the paper we're using, a Nav Ultra and a heavier Conqueror paper, the rotor length, the body width, the clip on or off, and the dropping technique. You hold it by the bottom or you hold it by the top. When you release it, it does make a difference. Working through the analysis, the half normal plot is a tool that we use for factorial designs, especially 2-level factorial designs. You can see that the drop and the clip stand off from the noise in the subplot effects. And we made a judgment call based upon subject matter knowledge that supports this paper by clip interaction. It was believed that the heavier paper is less affected by having the clip on or off. For the hard-to-change factors, the construction effects, the length of the rotors determines the flight time. And then paper on its own is insignificant, but it's in the model to support the hierarchy of this interaction. Basically, if you have an interaction, you want to make sure that you have its parents in the model with it. Paper has an effect, it just depends upon whether the clip's on or not. Nothing's different there from our normal analysis. The ANOVA is split into 2 parts. You have the hard to change factor effects that are tested as part of the whole plot section. And then the easy to change effects and interactions are tested as part of the subplot section. If there were paper by rotor interactions, they would appear as part of the whole plot. But paper by clip interactions are part of the subplot. The rule is pretty simple. If it includes an easy to change factor, it's tested as an easy to change factor. Something that generated that effect was reset every run. Up here, whatever generates the effect is only reset between groups. I like simple rules. So long and short, the winner was a situation where the clip was on. The paper type was set to the heavier Conqueror paper. The drop was from the bottom. And then these tail width things, the tail length and tail width didn't make much difference. However, the rotor needs to be long to generate this plot. So what if dropping the helicopter was destructive? Now, I'm not talking completely destructive, but maybe there's some wear and tear when you drop it so that the succeeding drops will be a little bit shorter. The wings fold flatter and it falls straighter. Randomizing the easy to change factors provides some protection against this bias. It's still there, but we're not going to necessarily assign the wear and tear factor, if you will, to one of the easy to change factors. That's what randomization does for us. It helps prevent a lurking variable from contaminating our analysis. If we did full randomization, 1 helicopter per run, then we won't have the fatigue problem. So think about it. We chose to not randomize to a helicopter every run because it was hard to change. It takes a long time to build those helicopters. We had 16 unique helicopters. Basically, that's 8 with each paper. If you were to look at a completely randomized design using our min-run characterize designs, that would require 22 unique helicopters. Is it worth doing 6 more helicopters to get a completely randomized design? I leave that to you to judge. What you get for doing a completely randomized design is you have more power to detect the helicopter. It has more power to detect the helicopter construction factor effects. So if you're really concerned about, do all these construction factors matter? Probably should just go ahead and randomize them. It depends on what's most critical to you. However, it's going to have less power to detect the dropping technique effects. The reason for that is any noise that comes from constructing the helicopter. If we use the split plot structure, we can separate those noises. Just test the dropping technique against its own noise, and then the construction technique against total noise. The other thing to think about is it's 22 runs and 22 builds versus 32 runs with 16 builds. That's 10 fewer trips up the ladder. So the relative powers, if you had small construction effects, but those were important to understand, doing your 16 groups reduces the power down to just a little under 61% for the hard to change main effects. However, we have lots of power because of the partitioning of the noise and the fact that this is being compared across 32 runs. If we were to use the 22 helicopters design, note the difference. It's 6 more helicopters but 10 less drops. Fractional factorial designs are awesome. Then we only get 63% power for these easy to change effects for the dropping technique, but we get 63% power for the hard to change factors with 10 fewer total runs. You have to think about this cost versus information problem. Whenever you're restricting the randomization, I encourage you to explore fractional factorial designs that can still give you the information you need. They compare favorably on power. One last example. A transport truck example of a split plot. It's based upon my experiences helping the United States military do experiments. So in this case, we have a maker of a wheeled heavy transport vehicle that wants to demonstrate fuel efficiency gains from their new transmission. Convince the military to buy and install many more transmissions. It's also suggested by another group who's trying to keep costs down that cheaper tires can be used on the heavy transport vehicles to reduce the overall costs. If we manage to combine the two factors, that results in 6 possible combinations. There's 3 levels of the tire. Whenever you're doing a two-factor design, you need to replicate to improve the power and provide enough information to get some estimate of the noise so you can test the effects. Whenever I'm in a situation where I'm being forced to replicate to improve power, I always think, well, rather than replicating, why not add another factor? Put it out there. Let people brainstorm about it. Is there another factor we want to try and test, seeing as how we only have two factors and need to replicate anyway? Well, it turned out in this case that someone thought, well, there's different payloads that we can put on this truck, and that will change the effect of both the tire and the transmission, which is the very definition of an interaction. So a light payload, an armored personnel character, weighs about 20 tons versus a main battle tank, which weighs about 70 tons. It's almost like getting something for free. It's a trick that I play when I'm doing consulting. However, there's two trucks set aside for this experiment. One truck will receive the new transmission, and the other will receive a refurbished old transmission. When this happens, we're really going to be testing truck 1 with a new transmission versus truck 2 with the old transmission. This means we are assuming the trucks are the same as each other and representative of the population of trucks. If the trucks are not the same, then what we think we've got for a transmission effect might be just the truck. Or worse, if we put the new transmission on a poor truck, it might wipe out any transmission differences that exist. So you have to be careful. This is a situation where you're not resetting. So the experiment's going to work like this. We start with one of the trucks, and it will start the course. And when it gets about halfway around, we start the other truck. When the truck gets back, we'll unload the payload, change the tires. There's a lot of them. And the same tires might get put back on. Then the payload will be reloaded, and it could be the same payload. And then the truck gets sent out on the next run. Sometimes that reset isn't practical. As you notice that I'm not touching the transmission. New helicopters were constructed for every group. Distinct fields were prepared with different fertilizers and irrigation in the one example. And as I mentioned, with the furnace temps, there's a natural reset. You open the door, a treated batch comes out, a new batch goes in, the temperature dial is turned to reset, and then back to the desired temperature. However, once a transmission is installed on a truck, it won't be swapped between trucks or even reinstalled on the same truck. It's matching how the process really works. The transmissions do not get reset between delivery missions. This eliminates the hard-to-change factor reset noise. And it's only a good idea when the population is when this is a representative of the population. You should always plan for a reset between groups. And only experiment without resets when it's absolutely necessary. So 2 transmissions, 3 tires, and 2 payloads makes for a 12-run group. The problem is, if you only do this once, you won't be able to test. Well, the power is going to be very low. I determined that it actually takes 48 runs to get the power to an acceptable level for a 2 standard deviation change. However, I don't want to run 24 hours a day to get this done. I'm going to basically do my 12 runs and then stop. So each replicate is going to take place on its own day. The same 12 runs will be conducted within each day. Sound like I'm restricting the randomization even further? Because I am. But instead of making day of the experiment another hard-to-change factor, it's going to be blocked. And the way I think about it is I determine whether something can be treated as a hard-to-change factor by answering the question, can it be replicated? So with the day-to-day variation, can the setting of June 16th, 2014 be replicated once we get to June 17th? Not without a time machine. So we end up blocking the day-to-day variation from influencing the analysis. And the word block has 2 meanings. The first meaning is literally the kind of block that stops something from happening. I'm blocking you from biasing my analysis with your extra noise day-to-day variation. Or you can think of block as a group of its own, a block of runs that take place each day. Now the truth is, anything that's changing during an experiment that you're aware of and is not a factor of interest can be set up as a block. There are, of course, a few exceptions to that. The main one being if what you're blocking on interacts with the factors of interest, then you probably should be including that as a factor rather than a block. So wrapping this up, not randomizing increases the risk of confounding a factor change with a lurking variable. That's true whether you can randomize the groups or not. Holding everything constant for each group increases the risk of confounding with a lurking variable on those hard-to-change factors. If you choose not to reset between groups or even between runs, you can bias the estimate of the noise, which will in turn bias the statistical tests. That reset is the key to running good experiments, split plot or not. And if you don't separate the noise, testing like everything was randomized, or randomizing a difficult to reset factor, then you can get a misleading model. If you test hard to change factors as though that were run in groups as though things were randomized, you're going to be more significant than you should be on your tests. You may detect effects that aren't really there. And versus going the other way, if you don't take care of the noise that comes from the hard to reset factors by setting them up in groups, it can wash away the effects of the easy to change factors. If you're interested in getting more information on this, we do have a new workshop, Factorial Split Plot Designs for Hard to Change Factors. It's offered as a half-day extension on our Experiment Design Made Easy workshop. And of course, we can come teach it at your convenience. Take a look at our website. There's lots of information out there. Use the help in the software. It can answer many of your questions directly, including about these split plots. And if you have questions that are probably historical in nature, they can usually be found on our forum. It's a read-only forum, but that's where we put our most commonly asked, frequently asked questions. You can always send us emails as well. Most of you get the Stat Teaser or the bi-monthly FAQ alert, which is how you learned about this webinar. Thank you for attending. Let me know if you have any questions. I will stick around until either the questions are all answered or everyone logs off. Thank you very much for your attentiveness. Table for the, I can do that. Okay, so the design for the truck example had days, groups within days, two groups within days, with a random truck pick to start the day. The next question is a good one. Minimum number of whole plots. Well, same rule as for building a design. What's the minimum number of runs? You need one run to estimate one term in a model. And then you need some extra runs in order to test that model. So if you think of this transmission type, that's one run, that's two runs. I then had to do an extra replicate so that I could test the effects of the transmission. And then I had to do extra to get power to detect those effects with a reasonable chance. So in this case, I needed 2, 4, 6, 8 groups. If you have two factors, then you've got a main effect for each factor and an interaction between those two factors, plus the overall intercept. So that requires 4 runs to get the estimates, and then 4 more runs, groups. Runs and groups are used interchangeably here, to get the test between those groups. So probably a minimum of 8. Now there's fractional designs that you can build that have less than all possibles. You can build to only estimate the two-factor interactions, such as when you have 4 hard-to-change factors, you can fraction it. And yes, this will be posted as soon as we get it recorded. We will store it up there as soon as we get a good recording that works. Should be later this week, possibly next week. Next question, how are split plot designs made in DX? We have essentially 3 kinds of split plot designs that we can work with. Right now they are limited to factorials. Next version, maybe second version from now, we'll be adding response surface designs and maybe even combined designs. But right now we have a regular 2-level. So the helicopter experiment was this. 6 factors, 4 hard to change, 32 runs. full factorial for the hard to change, half fraction for the whole design. Multi-level categorics was how the truck example was built. One hard to change factor, two easy to change factors. There was 3 levels, and that would do all possible, in this case 12 combinations. And then there is the optimal, which will let you do fractions for when you have more work to do. For the regular 2-level, it does indeed have a minimum of 3 factors. If you need to do 2-factor designs, use multi-level categoric, and you can leave them both as 2 factors. Comparing powers is a good question. Really, you have to build designs side by side and compare them. We don't really have the ability to do 2 designs within the same instance, but you can open up 2 instances and compare them side by side. Something like that. Hard to change factors should be set to either categorical or numeric to match what you're doing with the experiment. Numeric indicates that you were interested in predictions between the extreme settings. The limit right now is, in Design Expert, is we have factorial designs, which are really only useful for estimating linear effects and interactions. Categoric or numeric doesn't make much difference to these designs. That's why we did them first. The response surface designs are coming soon. I don't know exactly how soon. As soon as we can do it. Many of the reasons we don't have farmer-related examples is pharmaceutical companies won't publish their results. So we'd have to make the data up anyway. I could do the truck example as pharmaceuticals. Change transmission to grinder. Change easy to change as API instead of load or payload. It's all the same basic design. But the main reason we don't have more pharma examples is there aren't any. They get published where we can read them. Something about protecting trade secrets. As I said, split plots for RSMs are coming. We can't build them currently, but we can analyze response surface designs. They just need to be set up, the groups matched up to the hard to change factor setting changes, and then you can analyze it using the same techniques we have. What we're missing is the build. Okay, question about the 2 standard deviations. What I believe you're talking about, I have to get the model set, is 2 variances here. Well, you have one variance that's associated with the hard-to-change factors. It's the variance caused by resetting the groups. That's one partition, and then the residual is the remaining unexplained variation that exists in the split in the subplot group. Excuse me, subplot runs, the run-to-run variation. This partitioning is what's driving what's going on with the temperature test. There's a much more error here. You'd need a much larger temperature effect for it to be significant on its own, versus the very small residual error for testing the coding and this coding by temperature interaction. That's the dual error nature. One error from the hard to change, one error from the easy to change. Which should also answer the question about why factors are hard to change factors have less power. There's fewer runs. Oh, okay. Another question about the presentation itself. Get it back up. I used different power when I was talking about the helicopter, different noise situation when I was talking about the helicopter. Coming up soon. Okay, someone noticed that I had a sigma here of 1 and a sigma here of 1.41, which is the square root of 2. The reason I did that is because this sigma applies to the residual. This isn't this. This is the subplot. Excuse me, the subplot noise. I should be on the noise. And I, by default, use a situation when I'm building a split plot where half of the noise is attributed to the hard to change and half is attributed to the easy to change. When I want to test against a other design, I need to put those two noises back together. So you take the two variances, add them together, and then take the square root. So if the noise for the easy to change is 1, the noise for the total is 1.41 or square root of 2. Have we gotten to your question? If we have not, please ask it again. I think I answered everybody, or Brooks. Okay, again, trying to understand the power differences. The hard to change factors are changed less often. There's less information to test them against. The easy to change factors are changed more often. So there's more information to test them against. That alone would explain some of this difference in powers. In addition to that, These easy-to-change effects are tested against a smaller noise than the hard-to-change effects. This noise is only applied over here, and then it's essentially doubled, take the square root of the double, for testing the split plot designs. There's two sources of variation that get combined when you test the hard-to-change factors. So that's the difference between the two powers. Is that better? All right, if there's no more pressing questions, I'm going to go ahead and end the webinar. Thank you all for attending. If you do have any lingering questions, you can send them to our help@statease.com address, and we'll be more than happy to answer them offline. Thanks again.